Hello! We now look at applying Meyerson's lemma to cases where ideal auctions are not possible. Recall that an auction is ideal if it is DSIC, welfare maximizing, and efficient. We now consider an auction that cannot be ideal. Suppose we are managing advertising slots for a TV station. We have T seconds to fill, and there are potential advertisers N. Advertiser I has an ad of length Ti seconds, and they get a value of Vi out of it. We then run an auction to determine which ads to air. Take a look at this small instance of the problem. We had 10 seconds to fill, and 4 advertisers with ads with different lengths and different values. We are picking a number of ads to fit into this 10-second time slot, so each ad is either picked or not picked. We can then think of the set of feasible allocations as all the 0, 1 vectors over n, which we call x, such that the sum of Tixi, which is the sum total of the time of the winners, is at most t, the amount of time available. In our example, we could fit the first 2 ads into our 10-second time slot. The social welfare is then the sum of all the values of all the winning ads, which is the sum of Vixi. In our case, our social welfare is 20 plus 56, which is 76. To maximize social welfare, we need a max of V transpose X, where X is in our set of feasible allocations. Now recall that the first stage in designing this auction is to assume players bid truthfully and find an allocation rule that is welfare maximizing. Then, Meyerson's lemma gives us a payment rule that is DSIC. Except there is a problem here. The problem is that maximizing social welfare here is equivalent to the knapsack problem. In the knapsack problem, you have a knapsack that can carry a certain amount of weight. There is a number of items, each with different weights and different values, and you are trying to pick items that fit into your knapsack with the highest value. And the knapsack problem is famously NP hard. This means that it is not possible to find an optimal solution efficiently, unless P is equal to NP, which is generally believed to be false. This means that we cannot fulfill both 2 and 3 in the criteria for ideal auctions simultaneously. In order to guarantee welfare maximization, we cannot have an efficient algorithm. If we want an efficient algorithm, then we cannot guarantee that our solution is welfare maximizing. So, what is the solution here? We need to relax either 2 or 3, meaning we should give up on one of these 2 conditions. But we should not be giving up number 3, which is efficiency, as we want this to be practical and be run in real time. So, we need to give up on welfare maximization. Instead of finding a welfare maximizing allocation exactly, we will find an approximation of the allocation that is close to the maximum, while keeping efficiency. Recall that Meyerson's lemma does not really require welfare maximizing allocations. It just requires that the allocation is monotone. So, as long as our approximation is good enough and monotone, we can apply Meyerson's lemma to get a DSIC payment rule with respect to our approximation. And we will look at one possible approximation to the knapsack auction problem in the next lecture.